I want to welcome you all to lecture number 4 in this 6-part lecture series on climate change. And I particularly want to thank Wave Street Studios for putting this on, and Rhett Smith, the owner of Wave Street. Thanks so much for showing me so much hospitality and setting this up so nice. I also want to thank my dear friend Katie Shane for suggesting this series about 6 months ago. It's been a lot of fun. Well, we're now on lecture 4, Technologies and Practices for Halting Climate Change, part 1. And just for a quick review, we've completed 3 lectures over the last 3 weeks, and we pretty much finished with the science tier. Now we're moving up into the technology tier, and we're here on lecture 4. And I'm going to be relying heavily on material presented by Project Drawdown. I'm going to cover about half of that today, half of it next week, and talk about a few additional things, some Bill Gates' recent book and that sort of thing, talk a little bit about geoengineering. And finally, in the final lecture, in 2 weeks, lecture 6, we'll be finally winding up talking about policy. But first, I want to very briefly review a little bit of the science we talked about on the last couple of lectures. And this is a graph you may remember. 3 lines on here. The black line is the observed temperature. The brown line is the simulated temperature of the Earth using an ensemble of climate models. We talked about that last week. It's a group of climate models using all the physics for both simulated, both human and natural climate change. And finally, the green line here is using the same climate models, the same climate model ensemble. We're simulating climate change, the warming from 1850 to 2020, using only natural variability, only the effect of the sun and volcanic activity. And what we see here is that beginning about the mid-70s, the Earth begins to warm dramatically. The models which incorporate greenhouse gases, the human emissions of greenhouse gases, capture that warming very accurately. This is a hindcast from 1850 to 2020. And the models predict that warming extremely accurately within a few tenths of degrees. When you incorporate the human emissions of greenhouse gases, when you ignore the human emissions of greenhouse gases, pretend that they don't exist, pretend that the greenhouse gases just basically remain stable, then you get this result down here, clearly wrong. And that is a very clear indication that the human emissions of greenhouse gases are driving the global warming and climate change that we are concerned with. Now, I want to introduce one additional new science issue, and it's called radiative forcing. Now, we talked extensively in the first 2 lectures about that radiative balance at the top of the atmosphere, the Earth's energy imbalance, EEI. Well, radiative forcing is a related term. It's a little bit subtle, and it goes like this. Radiative forcing, basically expressed in watts per square meter, tells you the effect of each greenhouse gas on that radiative imbalance at the top of the atmosphere relative to 1750. 1750 is taken as a reference year, pre-industrial. So basically, all of the radiative forcing for each of these constituent gases here, and you recognize these as the greenhouse gases, and these are the F gases we talked about, the fluorinated gases, 3 different types of fluorinated gases. If you extrapolated this bar chart back to 1750, it would collapse down to 0, because we're arbitrarily assuming that the radiative forcing is 0 in 1750. That's the pre-industrial era. Now, in the case of carbon dioxide, yes, there was carbon dioxide existed in the atmosphere back then. It was trapping radiation, but we're not really concerned with that amount of radiative forcing. What we're concerned about is how has it changed over the course of the industrial era. So it's all referenced to 1750. And you can see what's happening here. You know, it's going steadily upward, such that by 2020, we were experiencing radiative forcing from these greenhouse gases of 3 watts per square meter relative to what it was in the pre-industrial area. So the greenhouse gases have produced additional warming of 3 watts per square meter. Now, I know what you're thinking. You're remembering one of the charts we talked about in prior lectures, and we talked about EEI, the Earth's energy imbalance, that imbalance of radiation at the top of the atmosphere. And we talked about it was about 0.9 watts per square meter, about 1 or a little less than 1 watts per square meter. And here now I'm telling you 3 watts per square meter. So what is the discrepancy there? Well, the discrepancy actually is another thing we talked about, and that is that negative feedback, that long-wave radiative feedback negative feedback. As the Earth has warmed, you remember that relationship that said the radiation from the Earth was proportional to the Earth's temperature to the fourth power, and that caused additional cooling. Well, in fact, it's that additional cooling as the Earth has warmed about 1 degree centigrade that compensates for this additional forcing of 3 watts per square meter. So it does come into balance there. And it's good, like I said in that lecture, that we have that negative feedback, because if we didn't, then the Earth would be warming about 3 times as fast as it is right now, about 3 watts per square meter warming, as opposed to about 1 watts per square meter. Also from this, you can see that indeed carbon dioxide is the dominant greenhouse gas, and you can see how rapidly it's increased. Back around 1979, it was producing warming of about 1 watt per square meter relative to the pre-industrial era. And now it's up around 2. It's doubled. Its impact on global warming has doubled over this time period. And you can see the relative impact here. It's carbon dioxide, methane, the fluorinated gases, which are the combination of all these 3 here, and finally nitrous oxide. So that's one thing, radiative forcing. Now there's another term I want you to remember, and that's Annual Greenhouse Gas Index, or AGGI. AGGI is a NOAA product put out by the NOAA Earth Systems Research Laboratory, and it's just a very simple way of looking at how this radiative forcing increases over time. Like the radiative forcing, it's referenced to 1750. So this index value goes to 0 at 1750, just in the year 1750, just like the radiative forcing does. But then it's referenced to 1990, such that AGGI is defined as 1 in 1990. And then that being the case, we find that in 2020, it was at 1.47. What that means is, it's a simple way of looking at it, what that means is the total radiative forcing increased by 47% since 1990. Why choose 1990? Well, 1990 was chosen because that's the baseline year of the Kyoto Protocol, which we're going to talk about in the last lecture. And it's also the first year that the IPCC, the Intergovernmental Panel on Climate Change, released its first report, its first assessment report. So arbitrarily, 1990 is chosen to have an AGGI of 1. Everything is referenced to that. So we see that here in 2020, the total warming due to these greenhouse gases had increased about 47%. Now in 2021, it's 1.49, so it's increased an additional 2%. Okay, so the idea here now is we need to reduce this increase in these greenhouse gases, mainly focused on carbon dioxide. You can see it's the biggest contributor here, but we do have to deal with all of the greenhouse gases here. Carbon neutral, what does that mean? Well, carbon neutral would be we've reduced the emissions of greenhouse gases and we've enhanced the ability of the natural world and even possibly artificial means to remove carbon dioxide from the atmosphere, such that this curve would flatten out. It would flatten out. And you would no longer have these bars going up. And then we would hit the point of drawdown, hence drawdown.org we're going to be talking about. And that would be the bars are actually coming down from carbon neutral point. And that's what we need to get, that's what we need to do to get where we need to be. And so the rest of this talk is going to be focused on what is it going to take to get there, to do that kind of thing. But before I get into that too much, I want to talk about where the greenhouse gases are coming from. And this follows the drawdown.org sort of paradigm for talking about different sectors that emit greenhouse gases. And this is a global picture, not a US picture. And number 1 is electricity production. About 25% of greenhouse gas emissions have to do with electrification of the power grid globally. Close behind that is food, agriculture, and land use. Then industry, particularly steel and cement production, but also plastic production. Finally, transportation, about 14%. If you remember that picture we looked at for the US, transportation was much higher. Transportation was actually number 1 in the US. It was over 25%. Globally, transportation is much less. We drive a lot of cars in this country. We drive a lot of big cars. We have wide open spaces, lots of shipping. But globally, transportation is actually pretty far down. And then it's buildings and other sources here. So with that preliminary out of the way, I want to talk about Project Drawdown. Project Drawdown is a nonprofit organization that proposes, analyzes, and ranks solutions for reducing greenhouse gases in the atmosphere with the goal of reaching drawdown, which we talked about, gases actually coming down. It was founded in 2014 by Paul Hawken and is currently headed by Jonathan Foley. Project Drawdown presents about 80 solutions for reducing greenhouse gases by avoiding emissions and/or by sequestering carbon dioxide and other gases already in the atmosphere. The solutions consist of technologies and practices organized into 9 sectors and implemented in 2 scenarios. Scenario 1 is hold global warming by the end of the century to 2 degrees centigrade warming. Scenario 2 is hold global warming to 1.5 degrees centigrade warming, the 2 goals of the Paris Climate Accord. It also includes analysis of global cost and return on investment for each solution. That's one thing that makes this such a powerful thing. It's not just presenting the science and the technology, but rather it's doing careful economic analysis to see what the economic benefits are of this. Drawdown essentially provides a roadmap for stopping and eventually reversing global warming and climate change. Drawdown builds themselves as the world's leading resource for climate solutions, and I agree. I think they're really excellent, and that's why I've chosen them to kind of highlight for this talk. By the way, you can go on their website, which is excellent. There's lots of material there, but you can also download their latest publication, Drawdown Review 2020, and it's a wealth of wonderful material, highly worth looking at. So I mentioned the economic analysis. So for Drawdown scenario 2, which is hold global warming to 1.5 degrees centigrade, which is the most stringent goal of the Paris Accord, here's what they analyzed the costs are. The annual cost of the world over a 30-year period. Annual cost of the world by year over a 30-year period, $1 trillion per year, which totals to about $30 trillion over that 30-year period. Sounds like a lot of money, but in fact, it's only about 1.25% of global GDP. Now, most of that money would be spent up front, but if you prorate it over the 30-year period, it works out to be about $1 trillion per year, which is 1.25% of global GDP. But here's the thing, there's a return on investment. In fact, it's about a 5-to-1 return on investment. And I'm not talking about cost savings here. I'm not talking about cost savings that we hold the hurricanes down and as a result we have less damage, but rather it's just cost savings having to do with, for example, you replace a gas-fired power plant with a solar array or wind turbines, and it's much cheaper. It's cheaper to implement it, and it's cheaper in the long run because the fuel is free. Now, if you prorated these costs over each country's GDP, that would equate to about $250 billion per year for the U.S. over that 30-year period, which is about 1.1% of global of U.S. GDP. That's a pretty big number. That's about half of the defense budget, or maybe a third of the defense budget. 1% of global GDP. It's far larger than the amount of discretionary spending that's typically available in the U.S. budget. But look at the return on investment. You're investing $250 billion per year, but you're getting a return on investment of about $1 trillion per year. And by the way, this investment is not necessarily coming from the U.S. government. Some of it would be, but not all of it. Much of it will be coming from private industry, even individuals. You're going to buy rooftop solar for your house and that sort of thing. So, but the other thing is, it's important to take a look at issues I talk about down here. There's a huge amount of money that's going to the fossil fuel industry from the U.S. government and from all governments of the world. According to the International Monetary Fund, the global fossil fuel industry is currently subsidized at about $5.2 trillion per year, or about 6.5% of global GDP. That's huge. Just a small fraction of that, and you could cover what needs to be done. Again, according to the IMF, the U.S. fossil fuel industry is currently subsidized at about $650 billion per year. Now, this is a controversial number. If you ask the oil industry how much are they subsidized, they're going to say it's really low, hardly anything. If you go to environmentalists, they're going to say it's really high. This is low. I chose the IMF. I kind of consider them to be an honest broker here. But even if it was a half or a third of this amount of money, it's still a lot of money to work with there. Now, does the U.S. government write a check for $650 billion to the oil industry every year? No, it doesn't work that way. What we're talking about here are subsidies and tax breaks that are deeply embedded into the tax code. Deeply embedded and almost inscrutable. It's things like drilling incentives, oil field depletion allowances, huge amounts of incentives that are scattered through the tax code. Well, why don't we just remove them? Well, you know, you've got an army of, you have a very, well, richest companies in the world. You know, the oil companies are some of the richest companies in the world, and the question on the table is, why are we still subsidizing? Why do we subsidize in the first place? Well, there's a good reason why we subsidize them in the first place. You go back to the 70s, what you find was there was the oil crisis, which I think all of us, many of us probably remember, but not all of us in this room. And suddenly we woke up and there was something called OPEC, and suddenly there were gas lines, you know, going around the block here. And so the U.S. said, we've got to increase our ability to produce domestic oil and energy. And so the Congress moved into action and produced all kinds of incentives to incentivize the domestic oil production and gas production. And it worked. You know, we now are the world's largest exporter of energy. We are energy independent. It worked. And the companies, the oil companies in the interim period, became some of the richest and most successful companies in the world. So the question is, why are we still subsidizing them? And the answer is, well, they're very rich companies, and they have an army of lobbyists in Washington making sure that those subsidies stay in place. They fund many members of Congress and U.S. senators making sure that subsidy is in place. So that's a tough nut to crack, but it's one that we do eventually have to crack, and we'll talk a little bit about that in the final lecture on policy. The other thing is, if you recall my prediction from the last lecture, my prediction was 2.5 degrees centigrade is where we're going by the end of this century. I stand by that prediction, but I'm going to tell you that scientifically and technically, we could achieve 1.5 degrees centigrade. The science says it's not too late to get there. The technology says we have the technology right now to get there. But I'm telling you, I'm still saying it's going to be 2.5 because I don't think we have the political power to do the things that need to be done, either in this country or around the world. So that's kind of where that's at. So here are the 9 Project Drawdown sectors. They organize their solutions around these sectors, and it's electricity, food, agriculture, and land use, industry, transportation, buildings. Those are those kind of that pie chart we looked at is organized along those lines. Health and education, land sinks, coastal and ocean sinks, and engineered sinks. So these are really geared towards reducing emissions of greenhouse gases. And the solutions here are oriented towards protecting and enhancing the ability of the natural world to remove greenhouse gases from the atmosphere. This is using artificial means to remove greenhouse gases from the atmosphere. And finally, health and education really is focused on limiting global population growth, which is an important part of this problem. So today, we're going to discuss these sectors. There's 80 solutions. We just can't get to them all in one day. But I do want to touch on every one a little bit. So we're going to talk about these sectors. And we'll jump right in on electricity. Now, the way I've organized this is, for each sector, I've put the ones that have the most impact up front. And so they're kind of ordered in amount of impact. And the impact is sort of described right here. You're going to see 2 numbers on every slide here. The first number is the amount of CO2 equivalent reduced or sequestered over 30 years in billions of tons. And this is the percent of CO2 reduction or sequestration required to hold global warming to 1.5 degrees centigrade. So what we're saying here is the onshore wind turbines part of these solutions actually accounts for 9.31% of where we need to be. That's huge. That's really huge. If you think about it, the average solution is 1.25% of the problem. It's 80 solutions, 1.25%. So the average, so you can kind of, you know, if you want to keep track, you can kind of reference this number to 1.25, which is the average solution. And you can see the onshore wind turbines are a big part of the solution, almost 10% just onshore wind turbines. So we have a really good example of onshore wind turbines here in California, and that is the Alta Wind Energy Center, which is located near Tehachapi, California. It's the largest wind farm in the United States and one of the largest in the world, with a nameplate capacity of 1,550 megawatts. Now, a couple engineering terms to come through here, talk about here. Nameplate capacity is a general expression about any power plant. And it specifies the amount of power the plant outputs under optimum operating conditions. So in the case of a wind farm, that would be the wind would be in the Goldilocks zone of between 25 and 50 miles an hour. Above 50 miles an hour, they shut down. Below 25 miles an hour, they're not producing all the output. And that brings up another important engineering term, and that's capacity factor. Capacity factor is the ratio of the long-term average of the power that the power plant produces to its maximum, to its nameplate capacity. Onshore wind turbines typically have a capacity factor of about 35% here. Now, another number, a good rule of thumb number to know is that 1 megawatt, a megawatt is a million watts of electricity compared to 100 watts for your light bulb, for example. 1 megawatt is enough power to support about 650 homes. So if you take 1,550 megawatts, multiply times 35%, realizing on the long-term average it's only producing about 35% of that nameplate capacity, multiply that times 650 homes per megawatt, you end up with this power plant being able to support about 352,000 homes. The next one is utility-scale solar voltaics. So solar photovoltaics can be implemented at utility scale, which is defined as 600 megawatts or greater, with thousands of panels to tap the sun's clean, free fuel and replace fossil fuel electricity generation. And it's large, 7.5%. We've already gotten up to over 17% with just these two solutions right here. And we happen to have a really great example of a solar farm pretty close to us, and that's the Topaz solar farm. Here's a picture of it viewed from space. It's located about 40 miles east of San Luis Obispo. It covers 9.5 square miles, which is the equivalent of 4,600 football fields, so it's really big. Has a nameplate capacity of 550 megawatts, making it one of the largest farms in the world. Topaz is owned by Mid-American Renewables, Berkshire Hathaway company. It sells electricity to PG&E, so very likely, if you're PG&E customers, you're getting some electricity from Topaz. So with a capacity factor of about 25%, which is typical of large-scale solar farms, it produces enough electricity to power about 89,000 homes. The next solution is distributed solar voltaics. That's rooftop solar panels. And of course, whether they're grid connected or part of a standalone system, they offer hyper-local clean electricity generation, and it's large, 4.32% of the solution. So now we're almost getting up to 20% of where we need to be with just these three solutions. Now, particularly with solar, we need to start talking about energy storage. So, for example, in the case of rooftop solar, you're talking about standalone batteries. For example, I'm hopefully soon going to get a Tesla Powerwall at our house. We've had solar array on there for about 8 months. Signed a contract about a year ago for a Tesla Powerwall. Hopefully it's going to show up this summer. And the idea there is it's being charged up during the day, and at night when the sun goes down, you play that energy back. So that's an important, I'm going to talk about a couple of enabling technologies here, and battery storage is one of them, beginning with distributed energy storage. The next is utility scale energy storage. Utility scale energy storage ensures electricity supply can match demand. It enables a shift to wind and solar power and curbs emissions from fossil fuel powered peaker plants that come online during periods of high electricity demand. The peaker plants are the most inefficient. They're the most expensive power on the grid. And these are plants that just kind of sit there and don't do anything until all of a sudden there's a need for additional power because everyone's got their air conditioners on or whatever, and then they kick into action. They're typically gas fired, and when you look at their levelized cost of energy over their lifetime, they're very, very, very expensive of power. So the idea of the utility scale energy storage, you can do away with those plants, but also you can take the huge amount of excess solar power we have during the day here in California, for example, and play it back at night. And we have a great example of that. In fact, we have the world's largest utility scale energy storage facility, stone throw away at Moss Landing. This is the Moss Landing power plant you recognize, Highway 1 right here. The Vista Energy Moss Landing energy storage facility is currently the largest in the world, with 1,600 megawatt hours of storage capacity and 400 megawatts of transmission capability. It's you drive along the highway, you can see it pretty clearly. It's located in this long building here, just before the actual decommissioned power plant. And also there's some external modules here. They plan to nearly double both by June of 2023. You may have read in the news about a year ago they had a casualty out there. There was it's actually a fire, but they had some kind of a meltdown event That's all been fixed, as I understand it, and they're going forward to double the size of this system, which is pretty amazing. So here's an interesting plot I just came by recently, and it kind of illustrates the importance of this battery energy storage capability. What we're looking at here is a plot over a 24-hour period. In fact, it is 30 April 2022, just recently. The curve here is the demand for electricity here in California over this 24-hour period on the 30th of April in megawatts. The blue curve here is the supply of renewable energy, and that's all renewable energy. That would be wind and solar and hydrothermal, hydropower and geothermal. And you can see, of course, when the sun comes up, so does the powers in renewable. That's basically the sun coming up and all the tremendous amount of solar power we have here in California. California leads the country in solar. And you can see this is the first time this happened. For about an hour, the supply from renewables actually exceeded the demand, which was the first time this has happened. And this, you can see how the demand curve works. It kind of actually hits a minimum in the early afternoon. It really peaks in the early evening, and then it goes back down overnight. So you can see what has to be done. We have to be able to, if we're going, and what's filled in here are, of course, the gas-fired power plants. What we need to do is increase the energy provided by renewables, but also we need that storage capability such that we can play back the excess energy we get during the day at night to basically narrow this curve right here. Right now, the space between these curves is part of the energy demands that renewables can't meet, and we need to get to a point where we can meet that and bring on additional wind turbines. Particularly offshore wind turbines will help because the wind doesn't stop blowing at night, particularly over the ocean. The sun does go down at night, there's no doubt about that. So we need to be able to store the energy during the day and play it back at night and basically bring this curve up such that it exceeds the demand. Grid flexibility. Smarter, more flexible electric grids can cut energy costs or losses during distribution. They are critical for renewables, which are more variable than conventional electricity generation. Generally speaking, the electric grid really needs a lot of work. We need to at least double it, perhaps triple it, as we make the transition to electrifying more and more in our economy. Right now, it's not up to it. But we also need to make it much more resilient and much more flexible to meet the new economy. Microgrids. A microgrid is a localized grouping of distributed energy sources like solar, wind, in-stream hydro, biomass, together with energy storage, the battery systems we were just looking at, or backup generation and load management tools. The use of local supply to serve local demand makes them much more resilient and reduces energy loss in transmission and distribution. So microgrids are an important enabling technology here. Okay, moving on to concentrated solar power. Concentrated solar power, different from photo PV or photovoltaics, concentrated solar power uses sunlight as a heat source rather than as an electricity source. And arrays of mirrors concentrate the incoming rays of the sun onto a receiver to heat a fluid, produce steam, turn turbines, and produce electricity. And pretty significant, about 1.5% of where we be, above the average for solutions. There's a great example of a concentrated solar plant down in Southern California. It's called the Ivanpah plant. This is one of 3 towers. There's actually 3 towers here, and these are all mirrors, you can see, and they turn during the day to focus the sun on this tower right here. It has it covers about 5.5 square miles, has a nameplate capacity of 392 megawatts. Capacity factor of about 22%, a little bit less than photovoltaics, and produces enough electricity to power about 56,000 homes. Concentrated solar power has one big advantage, and that is when the sun goes down, it doesn't stop. And that's because the fluid that turns the turbines is actually molten salt. So there's molten salt, it's heated up in here, and that's used to boil water, which turns a turbine just like a regular power plant does. When the sun goes down, the molten salt is still hot, and it stays hot pretty much all night long. In other words, you're storing the energy, rather than storing the energy from the daytime in a battery, you're storing it in this big container of molten salt. And as a result, these plants keep on generating power through the night, which is good. One big disadvantage of them is they really pretty much have to be in a desert environment. You have to be in a place where it's really, really sunny, really hot. Pretty much they're kind of relegated to the desert areas. Offshore wind turbines. A little bit less than the average here, about 0.72. But the winds over the sea are more consistent than those over the land, and offshore wind turbines tap into this power to generate utility-scale electricity without emissions. Very big in Europe, particularly in the UK. There's lots of wind turbines over there. I just saw a news article recently that the UK is getting ready to deploy the world's largest offshore wind farm. They're in the process of building it out now. Pretty big on the East Coast, particularly up in New England. Fixed bottom wind turbines. And as you may be aware, there has been proposed the Morro Bay offshore wind farm off of Big Sur between Lucia and Cambria, with the power coming ashore here at Morro Bay. This power plant, if it is built, will be huge. It'll have a nameplate capacity of 5,250 megawatts. That's 5.25 gigawatts. With the capacity factor of about 0.6, which is significantly higher than the onshore turbines. They operate at about 35% efficiency. Offshore wind turbines typically operate at about 60% efficiency because the winds are much more consistent and steady offshore. This will become, if it's built out, will become the highest capacity power plant in the state of California, capable of powering over 2 million homes. Now I keep saying if it's built out. It really kind of depends on who our next president is. The Biden administration has been very supportive of this, and the Department of the Interior, Secretary Holland, has been very supportive of this. If there's a change of administration, a change in the leadership in the Secretary of the Interior, then it's very possible this might not happen. But right now, it's moving forward towards the permitting, or towards the public discussion phase, and eventually the permitting phase over the next couple of years. If it does happen, it would happen deployment would begin. Latter part of this decade and probably be complete about 2030. So that's kind of the time frame we're talking about here. Geothermal power. Underground reservoirs of steamy hot water are the fuel for geothermal power. It can be piped to the surface to drive turbines and produce electricity without greenhouse gas emissions. Go to Iceland to see this. Iceland is the #1 country in the world for geothermal. They have a beautiful setup there. Lots of geology there. It's perfect for geothermal. But pretty big in California too, actually, because we have, not that far away, the geysers, which is the world's largest geothermal field. It's located in the mountains about 70 miles north of San Francisco. There's actually 18 different geothermal power plants distributed around there. Taken together, the power plants have a nameplate capacity of about 1,517 megawatts. Capacity factor is about 53%, so above the wind turbines, above the solar, but still not anywhere close to 100%. And they produce enough electricity to power over 522,000 homes. Part of our renewable energy mix. Biomass power. Biomass feedstock can replace fossil fuels for generating heat and electricity. Usually going to be using perennial biomass. And it's sort of viewed as a bridge solution to clean renewable energy production. Fairly small, 0.22% there. Small hydropower, again, very small. Think down by the old mill stream here. Good in certain locations, but not a terribly large part of the solution. Nuclear power. Okay, so I'm going to talk about nuclear power in some detail in Lecture 6, because I believe nuclear power is going to be probably the biggest policy challenge that we as a country are going to face. What are we going to do with nuclear power? Now, another thing you should know about Drawdown is they are really focused on technologies that exist right now. They're not looking towards technologies that are under development that might come along in a few years. They are talking about technologies that exist right now that we can deploy today. So that being the case, they are really talking, when they talk about nuclear power, second and third generation nuclear power plants, which are all the operational power plants we have out there now. They have a lot of problems, those plants, and I'm going to talk about it in detail on Lecture 6. What Drawdown doesn't talk about are fourth generation power plants. Bill Gates talks a lot about that in his book, and he's an investor in fourth generation. So the story doesn't stop here. When you look beyond where we are right now, and Drawdown doesn't do that. They purposely only focus on current technology. When you look at the fourth generation power plants, they significantly mitigate, not in my opinion, or in my opinion, they don't totally eliminate, but in my opinion, significantly mitigate the problems of second and third generation plants. So indeed, fourth generation plants could become an important part of the solution. There's a couple of advantages of nuclear power plants in general. Very high capacity factor, typically about 92% as opposed to 50, 30, 25 we've been talking about before. It means that once they get going, they're very reliable putting that power out. They have a very small footprint compared to renewable energy. You know, if you're talking about replacing this power plant with a wind farm or a solar farm, you're going to talk about 100 times the amount of space. You know, if this is, you know, a footprint of 2 square miles, now you're talking about 200 square miles. So there's a land use issue associated with renewables. Nuclear power has the advantage of being very compact, but there's a whole slew of problems which we're going to talk about later on. Generally speaking, drawdown, they regard nuclear power as sort of a regrets solution. It's one they think, well, you know, we kind of have to let it, you know, keep on going as a bridge to the future, but we don't really see, you know, investing a whole lot right now. I'm not sure that's the right answer, and I'll talk about that next 2 lectures. But anyway, they see it as sort of a temporary solution. They say nuclear power is slow, expensive, risky, and creates reactive waste. But it does have the potential to avoid emissions from fossil fuel electricity. Basically, it's a lot of carbon, zero carbon energy with a lot of baggage of problems. So we'll talk about it in more detail later. Ocean power, very limited. You can see that percentage here is very low. In certain places of the world, it can be an important part of the solution. That's things like tidal power, ocean current power, you know, like in a coastal area, maybe even wave dynamics. But it's a pretty small part of the total solution. So that was a whirlwind tour of electricity generation. Now we want to talk about food, agriculture, and land use. This is huge. Reduced food waste, 6.4%. That's huge. Roughly a third of the world's food is never eaten, which means land and resources used and greenhouse gases emitted in producing it were unnecessary. Interventions can reduce loss and waste as food moves from farm to fork, thereby reducing overall demand. This is kind of low-hanging fruit, you would think. You know, we're just throwing away too much food. We're just throwing away too much food. We're growing too much food and throwing it away. Plant-rich diets, also huge, close to 6% here of the solution. Shifting to a diet rich in plants is a demand-side solution to global warming that seeks to counter the meat-centric Western diet on the rise globally. And here's a famous statement you may have heard. If cattle were their own nation, they would be the world's 3rd largest emitter of greenhouse gases. Plant-based diets lessen demand for cattle and thus reduce greenhouse gas emissions. And here's a slide that kind of illustrates that. What we're looking at here on this bar chart is, on the curve here, is kilograms of CO2 equivalent for production of 1 kilogram of food as a function of different types of food. And you can see that lamb and beef and cheese, dairy, basically stick out like a sore thumb. It's huge greenhouse gas emissions here. And also, by the way, particularly beef production, very, very water intensive. Cattle farming consumes a huge amount of water around the world. Now, I can tell you, my wife and I have shifted to a plant-based diet a couple of years ago. And I got to tell you, part of that was for health reasons. As you get to be a certain age, then you got to be a little more careful what you eat. And you know, if you do a little research on that, you're going to pretty quickly come to a conclusion that eating, you know, farther down this end of the spectrum as opposed to that end of the spectrum is much more healthy. And there's a tremendous impact on greenhouse gas emission, on carbon footprint. If you're eating kind of down this end of the spectrum compared to the traditional Western diet, which is kind of down this end of the spectrum, it's a factor of orders of magnitude difference in greenhouse gas and carbon footprint. The problem is the rest of the world is shifting, as the rest of the world becomes richer, shifting towards the traditional Western diet. More and more people are consuming beef, dairy, lamb, and as a result, you know, that farming of those quantities are going up, and as a result, greenhouse gas emissions are going up. So I'm going to leave this slide with one recommendation to all of you, and that is ask your doctor if a plant-based diet is right for you. I bet he or she will say it is, because it is definitely a healthy diet. Peatland protection and rewetting. Peatlands, also known as bogs or mires, cover just 3% of the land surface, but store twice the amount of carbon held by all the world's forests. Protecting them through land preservation and fire prevention is a prime opportunity to manage global greenhouse gases. And you can see pretty large here, 2.6% of the total solution. Regenerative annual cropping. Building on conservation agriculture, we'll talk about in a second, with additional practices, regenerative annual cropping can include compost application, green manure, organic production. It reduces emissions, increases soil organic matter, and sequesters carbon, about 1.4% of the total solution. Improved rice production. It turns out rice paddies produce huge amounts of methane, and there are techniques for reducing that, about 8.87% of the solution. Indigenous peoples' forest tenure. What the heck is that? Well, think about the Amazon. You know, there's all this deforestation going on in the Amazon. That's a huge problem. And basically, the indigenous people of the Amazon are being pushed off their land, and in come the loggers. They rape the land basically, and have a huge negative impact on global warming and climate change. The idea of indigenous peoples' forest tenure is empower indigenous peoples in these forests around the world with stronger legal rights to resist that kind of thing, and therefore preserve these forests. Nutrient management, and again, part of farming. Overuse of nitrogen fertilizers, which is a very frequent phenomenon in agriculture, creates nitrous oxide. And more efficient use of the fertilizers can curb these emissions and reduce energy-intensive fertilizer production. Conservation agriculture. Conservation agriculture uses cover crops, aggressive crop rotation, minimal tilling, minimal disturbance of the soil in the production of annual crops. It protects the soil, avoids emissions, and sequesters carbon. Forest protection. In their biomass and soil, forests are powerful carbon storehouses. Protection prevents emissions from deforestation, shields that carbon, and enables ongoing carbon sequestration. System of rice intensification, SRI, developed in Madagascar in the 80s. It's a holistic approach for sustainable rice cultivation. It minimizes water use and alternating wet and dry conditions. It minimizes methane production and emissions, again, noting that rice production produces lots of methane. Grassland protection. Grasslands hold huge stocks of carbon, largely underground. Protecting them shields their carbon stores and avoids emissions from conversion to agricultural land or development. Farm irrigation. Pumping and distributing water is energy intensive. Drip and sprinkler irrigation, among other practices and technologies, make farm water use more precise and efficient. Sometimes you hear the term precision agriculture, and that's part of this. Sustainable intensification for smallholders. Smallholders are small farm holders around the world. And the idea, these practices can increase smallholder yields, which in theory produces demand to clear additional land. Practices include intercropping, ecosystem-based pest management, and equal resources for women. Pretty small here, but nevertheless part of the overall solution. So that was agriculture and land use. Now moving into industry. Huge. Refrigerant management. Remember we talked about the fluorinated gases and how the very, very unbelievably large global warming potential that the fluorinated gases have. Once they get into the atmosphere, they stay for tens of thousands of years. Some of them have global warming potentials in the range of tens of thousands compared to carbon dioxide, which is 1. So the idea here is to make sure that the leaks are managed, and that when devices are disposed of, such as air conditioners and refrigerators, that the fluorinated gases in them don't leak into the atmosphere. And that's huge, 3.6% of the overall solution. Closely related to that is the idea of alternative refrigerants. Fluorinated gases are not the only refrigerants available. Alternatives such as ammonia or captured carbon dioxide can replace these powerful greenhouse gases over time. And it's an important part of the solution, 3.18% here. Alternative cement. Cement production inherently produces a huge amount of CO2. And by the way, concrete is the world's most widely used material. There's more concrete used out there in the world than any other thing. And it's production of cement, which is an ingredient of concrete, is a substantial source of greenhouse gas emissions, generating about 5 to 6% of global emissions annually. So what can be done? Well, changing the composition of cement can significantly reduce these emissions, and that's about 1% of the solution. There are, in the longer term, other possible solutions such as carbon capture and storage at the plants that produce the cement, and we'll talk about those. The reason why Drawdown doesn't talk about those are future solutions. They're not technologies that are available right now. Methane digesters. Industrial scale anaerobic digesters control decomposition of organic waste and convert methane emissions into biogas, an alternative fuel, and digestate, a nutrient-rich fertilizer. Recycling. To produce new products from recovered materials requires fewer raw resources and less energy. Thus, recycling household, commercial, and industrial waste cuts emissions, about almost 4% or 0.4% of the solution. Bioplastics. Most plastics are made from fossil fuels, but bioplastics utilize plants as an alternative source of carbon. They often have lower emissions and sometimes biodegrade. Composting. Composting can range from backyard bins to industrial scale operations. Regardless, it converts organic waste into soil carbon, averting landfill methane emissions in the process. So composting is a good thing. Waste to energy. Waste to energy processes such as incineration, gasification, pyrolysis combust waste and convert it to heat and or electricity. Waste to energy plants create energy that might otherwise be sourced from coal-fired or gas-fired plants. Landfill methane capture. Landfills generate methane as organic waste decomposes. Rather than getting released as emissions, that methane can be captured and used to produce electricity. So there are devices that actually, put poles down into the landfill, and they actually extract the gas out of there, prevent it from going into the atmosphere. And we recall methane is a very powerful gas. It has a global warming potential of 28, which means, as we learned before, that 1 ton of methane into the atmosphere is like 28 tons of carbon dioxide. Recycled paper. Instead of relying on fresh timber to feed the paper pulping process and releasing carbon with each tree cut, recycled paper draws on existing material. Instead of releasing methane as it decomposes in the landfill, waste paper finds new life. Fairly small, but still part of the solution. Now, coastal and ocean sinks. Those were all talking about emissions. Now we're going to be talking about sinks here. Mangroves, salt marshes, and seagrasses sequester huge amounts of carbon in plants and soil. Protecting them inhibits degradation and safeguards their carbon sinks. So again, it's all about taking care of the natural world. Coastal wetland restoration, agriculture, development, and natural disasters have degraded many coastal wetlands, restoring mangrove forests, salt marshes, and seagrass beds to help revive carbon sequestration. Engineered sinks. Drawdown only talks about one. They talk about biochar production. Biomass slowly baked in the absence of oxygen becomes biochar. This is what it looks like right here. Retaining most of this feedstock's carbon, it can be buried for sequestration and potentially enrich the soil. What they don't talk about here is something you might have heard of, direct air capture. That would be devices that are actually machines that actually suck carbon out of the air. That's kind of a future technology. That's why they don't talk about it. That's something that Bill Gates talks about, and we'll talk about that a little bit in future lectures. Finally, health and education. This is all about holding down birth rates. Education lays a foundation for vibrant lives for girls and women, their families, and their communities. It is also one of the most powerful levers available for avoiding emissions by curbing population growth. And you can see it's huge, 5.38%. This is almost like wind turbines. It's really huge. And to get a feel for that, here's a plot of population of the Earth. Back in 1800, about 1 billion. By 1927, up to 2 billion. 3 billion in 1960, 4 billion in 74. We're now at about, or pretty close to 8 billion. We're about 7.7 billion right now. Projections are by 2048 going to 9 billion. And notice the curve is turning down. That's a good thing. And indeed, birth rates have been declining, which is a good thing. But it's going to be tough for the world to provide the food and water to support an additional couple of billion people. And climate change is going to make it worse. So holding down population growth is a big part of the solution. So I'll have some closing comments here, and then we'll open up to question. So these are the 9 project drawdown sectors, and these are the ones we discussed today. And I've put them in the top 20 ranking. The ones we talked about today are listed here. Where you see blanks, those are ones we haven't talked about yet. We're going to talk about them next week. And you can see the ones we talked about today, the top 5 are right there we talked about today. And number 1 is onshore wind turbines, followed by utility scale solar voltaics. That would be the utility scale solar farms. Reduce food waste, plant-rich diets, number 3 and 4. Of all the solutions, they're way up there. Health and education, keeping down population growth, is number 5. And then this rooftop solar is down number 8 here. Taking care of refrigerants, not throwing those air conditioners and freezers on the landfill. Peatland protection, concentrated solar power, and finally a type of agriculture, regenerative annual cropping. So those are the ones we talked about today. Next week we'll fill in the blanks here and have the full list of the top 20. And this is what we will discuss next week: transportation, buildings, and land sinks. Those are 3 big topics. And also next week we'll talk a little bit about Bill Gates' book, which I think is very good. I highly recommend it, How to Avoid a Climate Disaster. Gates takes very much a forward-looking view as opposed to Drawdown, which is focused on what can we do right now. Gates is talking about what can we do over the next X number of years. He talks a lot about direct air capture, carbon capture and storage, nuclear energy and so forth. So we'll try to get into that a little bit next week. But that's it for today. Thank you for your attention. And now we'll be open for questions and discussion.
Was that list that was about 3 or 4 slides back, are those current solutions, or are those all in the future?
These are current solutions. Basically, Drawdown is focused on what we can do right now. And if you go on the Drawdown website, you'll find a really good video series. It's called Drawdown 101. And I think it's 6 videos. It's Jonathan Foley, who's the CEO of Drawdown, speaking. He's very good. And if you go through that, it takes about an hour and a half, You go through those 6 videos, you'll see that he's very strongly pushing for what can we do with the technology we have now. We don't want to wait. We don't want just to wait for new technology. We don't want to wait for talk or tech. We need to do things now. Now they'll add additional solutions later on, and they're looking at those kind of solutions now and analyzing them. For example, eventually it's very likely that you'll see things on there like direct air capture, synthetic jet fuels, green hydrogen, those kinds of things, the kinds of things that Bill Gates talks about. Eventually Drawdown will get there. When it gets to the point where the technology is mature enough and commercially available, it can be deployed now. What Drawdown says, and I agree with them, the technology exists right now to solve the problem, to hold warming to 1.5 degrees and meet the goal of the Paris Accord. I say it's not going to happen, unfortunately, because we don't have the we in this country and people around the world don't have the political power to cut through the resistance to making the huge changes that will cause huge companies to have to change the way they do business. What else? Kyle.
Population control.
Yeah.
Is that what we're talking about? And how do you see that happening? Is that a voluntary thing, or is that something that your organization sees as a mandatory thing?
Completely voluntary. It's focused on improving the lives of young women and girls, improving their education, giving them other opportunities in the developing world mainly, giving them other opportunities, and also making birth control available. I'm sure that's got to be part of the solution as well. But it's not anything like China's mandate of you can only have 1 child per family, nothing like that. But rather giving people the opportunity, particularly in the developing world, to find other alternatives, to empower women to have their own careers and lives, and that has a tendency to hold birth rates down.
Realistically, what I'm looking at with women in different areas of the country is it appears that women are being somehow encouraged to have children through social monies being funded to have more babies. So how does that, I mean, I'm not having more babies, but for folks that are out there where money and healthcare, and you have a baby, you don't have to see that everything is provided for that child.
Yeah. I think birth rates in our country are actually pretty low compared to the global average, certainly low compared to the developing world. So I don't think it's so much focused on birth rates in our country, but I think it's focused on birth rates, in the global south, if you will, the developing world. Doug?
Yeah, at the beginning, when you showed the aggregate greenhouse gases, it looked like that methane hadn't increased much. It seemed to be pretty consistent over the years. Is that really the case, or is that just that they don't really have a good measure of how much methane is escaping into the atmosphere?
I think they have a pretty good measure. About the beginning of that slide, NOAA, boy, it's way back there. NOAA has a global monitoring network for greenhouse gases, and they have about 80 sites around the world that are monitoring continuously, and that's actually started back here in 1979. So I think we have a pretty good there's some uncertainty, of course, in any measurement, but I think we have a pretty good handle on it. So methane here, it's actually gone up. Back here it might have been like 1.4, say, and here you're right. It's about maybe 1.2. No, I take that back. Here it was about 0.4, right? From one, it's about 0.4. This is 1.5. Oh, and I'm looking at the wrong thing. Sorry about that. I'm not helping here. It looks like it might have gone up a little bit. I actually have, if you'll indulge me for a moment, I have another slide I didn't show that might be helpful here. And this is from the recent IPCC report. And what we're looking at here is emissions. These are not concentrations in the atmosphere, but rather emissions. And let's see, methane is the, good eye, Doug. You can see, in fact, methane emissions have gone down. Red here is emissions. And you can see back in 1990, 21%, 20%, 18%, 18%. So it's gone down. Yeah. It looks to me like. Or that's the rate of increase. I take that back. Yeah. The rate of increase has gone down, but in fact, emissions still have gone up. It's hard to say. It hasn't changed dramatically, but it looks to me like methane is still going up, but at a reduced rate of going up, if you will. Yeah. Mary Alice.
Are you familiar with Elon Musk's argument that one of the greatest problem facing the world is underpopulation?
I'm not familiar with that, and I don't agree with that.
I don't understand it. I was hoping you'd explain what he's saying.
I don't pay a whole lot of attention to Elon Musk. I don't understand that. I consider it to be one of the biggest problems facing the Earth. A threat to future civilization. No less than that. Everyone's probably aware there was that book, The Population Bomb, that came out, back in 70s, I guess. I haven't read that book. I'm not going to defend the author.
I think he's just referring to qualified people that he can hire.
Could be. Anyway, there's that book, The Population Bomb, and it forecasts all kinds of catastrophic things that were going to happen, and then they didn't happen, and so a lot of people say, well, that's the same with climate change. All these scientists are saying this is going to be a catastrophe, and they said the same thing about population. It didn't happen. Well, he had one part of his prediction was correct, and that was the population did explode. We saw that chart here, and he was pretty accurate in predicting where it was going to go. What he didn't foresee was the fact that global food production would keep up with that. Agriculture, particularly with use of, heavy use of fertilizers and so forth, has been able to barely, but has been able to keep up pretty much with global population. Now, recognizing the fact that there are billions of people out of the 7.7 billion people in the world, there's probably a couple of billion people that face food insecurity every day. No doubt about that. There's a lot of people in this country face food insecurity every day. So there's a limit to how far you can go with that. Right now, we pretty much maxed out agriculture. There's just no, a huge amount of the world's surface is dedicated to agriculture right now, and there's not much more places you can go. And, in many cases, the soil is pretty much burned out, pretty much tapped out from all the heavy use of fertilizers. So we're hitting a point where you're going to hit a brick wall where the food production is not going to be able to keep up with increasing population. And the predictions of the population bomb will very likely eventually come true. It just might take longer to get there. What about the oceans? Well, the oceans are going down as well. The productivity of the oceans are going down as the oceans are warming. We talked about, oxygen levels are going down, carbon dioxide levels are going up, ocean acidification. That's causing global fisheries productions to decline. Overfishing is a big part of it. Overgrazing. A lot of the problems are human problems separate from climate change, such as overfishing, overgrazing, and that sort of thing. So, at some point we're going to hit the wall, and that's going to be a big problem. Yes?
So this is for the 1.5 Celsius
Yes.
raise. And so
Right.
if you are setting the bar lower with a 2.5 Celsius raise,
Yeah.
then there's a little bit more flexibility in the path that we can go down to avoid that
Yes.
increase.
There's a little more flexibility and less money required, less money investment up front. I'll take whatever we can get. My prediction is 2.5. Right now, I talked a little bit about it last week about projections. Throw out some numbers. The Paris Accord said we need to keep global warming well below 2 degrees centigrade, and our target really is 1.5. Right now, we're on target for about 3, which is about twice the Paris goal. At the recent COP meeting, the Conference of Parties meeting, part of the IPCC, which took place in Glasgow recently, last fall. Companies renewed pledges, and if you total those pledges up, that would hold warming to about 2 degrees. My prediction is 2.5 degrees, because what will happen is those countries won't live up to their pledges any more than they lived up to the original pledges from the Paris Accord. We have the technology. Science says we can still do it. We lack the political power and will to do it, is where we are right now.
Do you see any way to shift that?
Well, I'm going to talk about that on the last lecture, based on policy, and I'm going to put a big pitch in for Citizens Climate Lobby, which I'm a member of. I'm actually the chair of the Monterey chapter of Citizens Climate Lobby. We've got about, I think we've got about 585 members. And Citizens Climate Lobby is a nationwide, it's actually global, and it's working very hard to try to move Congress, move the policymakers in the direction of where we need to go. And that's a grassroots kind of thing. I think there needs to be more grassroots efforts like that. As the impact of climate change becomes more apparent and more dire every year, that will help move the needle. That's a good thing. Also, I'm very optimistic about the younger generation. There are two things I'm optimistic about. I'm optimistic about the technology. We've got the technology to solve the problem. But I'm also optimistic about the millennial generation. When I give these talks, sometimes out at CSUMB, and I'm talking to students there, they really get it, and they're very energized to make change, and they're going to vote. And eventually, we'll have leaders in Congress and in the White House that will be able to solve this problem. The longer we wait, though, the harder the problem becomes. I'll talk about this extensively in the last lecture, but what's been happening is the fossil fuel industry has been trying to hold this back in much the same way that the tobacco industry tried to hold back regulation of cigarettes. They knew early on that cigarettes were a problem, so they spent hundreds of millions, if not billions of dollars trying to obfuscate the issue and trying to confuse the public, trying to bring what was settled science into question. The fossil fuel industry has done exactly the same thing, even employing some of the same PR firms to do it. And as a result, the needed change is being delayed and delayed and delayed, in much the same way that regulation of cigarettes was being delayed and delayed and delayed. So that's unfortunately happening.
It's all legal.
Yeah. Okay, I appreciate it. I appreciate everyone coming, and thanks for the great questions. And hopefully we'll see you all next week, same time, same place. Thank you.